So we're going to be talking about equations on vector planes in two-dimensional space for the first lesson, which means we're going to be talking about direction vectors. So a direction vector, so to define a line, we need at least 2 points or 1 point on the line and its slope. So the definition for a line, let's say L, a non-zero vector D is called a direction vector for the line if it is parallel to L. The line with the direction vector D is D1, D2. You guys are going to notice that the direction vector is just the slope of rise over run, so y over x, provided that D1 cannot equal 0, because their slope would be undefined. If D1 is equal to 0, then the slope is undefined and the line is vertical. Note that D1 and D2 are called direction vectors. So example 1, I want to find the direction vector for the following things for each line. So A, we have the line through the points -2 and 3, and through 4 and -1. So I'm going to have my line. I'm going to draw my point A, which is -2 and 3. So this is going to be A. B is 4 and -1. So my line is going to go through here. So I need to find my direction vector. So my direction vector is going to be this vector, which is AB. It's going to be this direction vector here. So the way we find it is simple. We just find the slope of the line. We get M is equal to y2 minus y1 over x2 minus x1, which is equal to -1 minus 3 over 4 minus -2, which gives me -4 over 6. And if I simplify it, I get -2 over 3, which means my rise is -2 and my run is 3, which means my direction vector is going to be 3, -2. So 3, -2 is going to be right over here. So this is going to be my direction vector. Now my next one is I want to find the direction vector for a line with a slope of 4 over 5. So I already have my rise over run. So again, M is equal to 4 over 5. This is my Y slash D2. And this is my X, which is D1. So my direction vector is just going to literally be 5, 4. And then we have C, a vertical line that passes through the point 6 and -5. So we have -6 and 5, which is over here, and I have a vertical line. So the slope of this line is going to be M is equal to 1 over 0, which gives me undefined. Therefore, my direction vector is just going to be 0, 1. So now we can develop an equation of the line using a point on the line and its direction vector. So we're going to talk about vector equations of a line. So for example, 2, I want to find the equation through the points P0, which is -3 and 5, with a direction vector of 1 and 2. So let's see what happens graphically. So my direction vector is going to be 1 and 2. So this is going to be my direction vector over here. This is my direction vector D. My PO is going to be -3 and 5. And 3, 1, 2, 3, 4, 5. So this is going to be my PO. And this is my D. So now I need to figure out how I'm going to come up with an equation of a line. So let's suppose a point xy is any generic point on the line. So let's say my pxy, let's say it's over here. So and then it's going to pass through these 2 points. So then we can say that P0 and vector P is equal to a scalar times my direction vector. Again, this is just a definition, so I will get to more examples of this later on. Let's see who came late. Who came? Mackenzie. Which means that if I take x plus 3, which is my first one, because if I isolate for x, I get x equal to -3, comma, y minus 5 is equal to a scalar times my direction vector, which is 1, comma 2. Or I can get my xy is equal to -3, comma 5 plus t times 1 over times 1 slash 2. So the use of different points on the line or a different direction vector will give various equations for the same line. So this is what is known as a vector equation. So the vector equation is a straight line in the plane that has the form x comma y is equal to x0 y0 plus t times direction vector 1 and the 2. So the resultant x and y is just the resultant or the vector r, which gives me the same thing. So this is where r, x, y is the position vector of any point on the line. So again, we can make a vector equation using any points on the line as long as we have p0 or p0. So x0, y0 is the position vector of some particular point on the line. So x0 and y0 we always have to have in order to create a vector equation. So d1, d2 is the direction of the vector line, and t is an element of the real numbers is the parameter. So t can be any real number. So we want to say the vector equation of the line through the points a, 1 and -3, and b, 9 and -2. So let's draw my graph, or let's draw my points. So 1 and -3 is over here. So this is going to be my a, which is 1, comma, -3. B is going to be 9 and 2, which is over here, 9, comma 2, which means that my line goes this way. So now let's figure out what my direction vector is going to be. So I need vector AB. So vector AB we can also find from what we did before, which is OB minus OA. So remember, head minus the tail, which means I get 9, comma 2 minus 1, comma 3. And this gives me a direction vector of 8, comma 5. So my direction vector is going to be 8, comma 5. So I'm going to have two equations. So I have my direction vector, which is d1, d2, and I can come up with a vector equation. So one of them is going to be xy. We're going to use the point B is equal to 1, comma -3 plus our scalar t times 8, comma 5, or we can write xy as vector r is equal to, we can use the point B, 9, comma 2 plus t times 8, comma 5. So these are vector equations. We're now going to learn about parametric and symmetric equations of a line. This mainly has to do a lot with algebra, so this part of vectors is pretty easy. So parametric and symmetric equations of a line are just another way of writing a vector equation of a line. So the parametric equation of a straight line in the plane has the form x is equal to the x points plus d1 times t. Y is equal to the y value of the point plus d2 times t, where d1 and d2 are direction numbers. Okay? So now if we rearrange the parametric equations of a line, for t we get what we call the symmetric equation. So this looks just like rational equations, just making them equal to each other, which you guys learned in advanced functions. So a symmetric equation can look like x minus x0 divided by d1, which is equal to y minus y0 divided by d2, where d1 and d2 cannot equal 0. We don't include the t because d1 and d2 are both multiplied by the scalar t, so we just leave it as is. So note the denominators in this form are the direction vectors. So our denominators are d1 and d2. Since any vector parallel to the line will do as a direction vector, and any point on the line can serve as the particular point regarding the equation, two equations may look entirely different, yet represent the same line. So let's do a specific example. So we need to ask, are the lines represented by the following equations coincident? That means, are they in the same straight line? Okay, or do they lie on the same straight line? So we have xy, so let's name this line 1, is equal to 1 comma 6 plus t times the vector 3 comma 2. And line 2 is equal to vector 4, 4 plus s times the vector negative 6, 4. So we need to check if the direction vectors are parallel. Okay, so that's our first thing. So from last unit, how do we check if vectors are parallel to each other? How do we check if vectors are parallel to each other? It's a something multiple of another. Starts with an S, ends in an R. So I need to find out if one vector is a scalar multiple of the other. So I have vector d1, or my first direction vector is equal to 3 comma negative 2. And I have my direction vector 2 is equal to negative 6 comma 4. So what we notice from here, my second direction vector is equal to 2 or negative 2 times the first direction vector. So because they are scalar multiples, therefore the lines can be coincident. But that's not all we have to prove. You have to prove something else as well. So now I need to check if one point on one line lies on the other. Okay? So what I mean by that is let's sub a point 4, 4. So let's sub 0.44 from line 2 into line 1. So because I have xy on the left side, I get 4 comma 4 is equal to 1 comma 6 plus t times 3 comma negative 2. If 0.44 lies on line 1, then I can say with confidence and prove that these lines are coincident and lie on the straight line, on the same straight line. So again, we take our x's and we come up with an equation for this. So I get 4 is equal to 1 plus 3t, and then I take my y's and come up with an equation with that. So I get 4 is equal to 6 plus negative 2t. So now I need to figure out what my t values are, and if they happen to be the same for both cases, then the point 4 and 4 lies on line 2, which means that these two lines are coincident. So I bring the 1 over, I get 3 is equal to 3t, which means t is equal to positive 1. Now on this side, I get negative 2 is equal to negative 2t, and t is equal to positive 1. As you guys can see, these are considered to be the same. So since both t's give me 1, that means that the point 4 and 4 lies on line 1. Actually, I think you're not on mute. There we go. And now we can say line 1 is coincident with line 2, which means that these guys lie on the same straight line. So now we're going to do a couple more examples. So now we have x is equal to 2 minus t and y is equal to 5t. So this is a parametric equation. And then we have x minus 3 is equal to 1 minus y over 5, and this is considered to be symmetric. So again, when we have nothing, when we don't have a denominator, we can only assume it's 1. It's equal to 1 minus y over 5. However, on the right side, I need it to be read as y minus a number. So what we need to do to the left side is multiply everything by negative 1. So this can be written as x minus 3 over 1 is equal to y minus 1 over negative 5. So now I need to figure out my direction vectors for both of these. So my first direction vector, so direction vector number 1, comes with my t values for my parametric equation. So I get negative 1, comma 5. My direction vector 2 comes from my denominators and my symmetric equation. So I get 1, comma negative 5. Now, in order for it to be coincident, I need to show that direction vector 1 is a scalar of direction vector 2 or vice versa. So I can say that direction vector 1 is equal to negative direction vector 2, which is true, because if I multiply my direction vector 2 by negative 1, I get direction vector 1 back, which is negative 1 and 5. So this proves that the lines may be coincident. Now, I need to prove if any of these points lie on each other's line. So I'm going to check the points from number 1. So this can be written as plus 0. So I got my x is 2 and my y is 0. So I'm going to sub in. So again, this is line 1. This is line 2. I'm going to sub in 2 and 0 for line 2. And I'm going to see if my lines are coincident. So basically, I need to check if my left side is equal to my right side. So my left side in line 2 is x minus 3. So I'm going to sub in 2 for x, so I get 2 minus 3, which gives me -1. So now I need to show that my right side gives me -1 as well. From what we can see, we can probably assume that that's not going to be the case. Is y minus 1 over 5, which gives me 0 minus 1 over 5, which gives me -1 over 5. Since I get two different values, my left side does not equal my right side, which means, therefore, point 20 does not lie on line 2. No, because it's 2 minus 3. For the right side, you mean 1 minus y? So 1 minus 0. Am I talking about this part right here?
Yeah.
Okay. Oh yeah, sorry, it's 1 over 5. My mistake. -1 over -5 gives me 1 over 5. Sorry.
Yeah, that's what I meant.
So the point 20 does not lie on line 2, which means line 1 and line 2, because they have their scalar multiples of each other, they are parallel and distinct. However, they are not coincident at all. They don't lie on the same line. Hopefully it's all coincident, right? If not, that's completely fine. Okay, I'm going to leave you guys the easy one. So C, I have an equation xy is equal to the vector 5, 3, 5, -3, plus s times the direction vector 2 and 1. And I have my symmetric equation x plus 5 over -2 is equal to y minus 3 over 1. So remember, the first step is to show that the direction vectors are scalar multiples of one another. If they are, proceed to step 2. If they're not, then you can assume that the lines are not parallel and therefore are not coincident. So take a couple seconds to figure out if these lines are parallel to each other. Okay, Priyanshu says they're not parallel. How about everybody else? You guys are probably like, sir, why are you giving us the easiest part of vectors last? Okay, does anyone else? Is D1 a scalar multiple of D2, or is D2 a scalar multiple of D1? Yes or no? So my first direction vector is 2 and 1. My direction vector 2 is -2 and 1. If I multiply my first direction vector by a negative, I get -2 and -1, which is not the same thing as -2 and 1, which means even if I multiply my second direction vector by a negative, I get +2 and -1, which is again is not the same. So D1 is not a scalar multiple of my second direction vector, which means the lines are not parallel or coincident. So guys, is this like 500 times easier than the first two vector units? Okay, I see three of you are awake, 4 of you are awake. I'm guessing the rest are asleep or have me on mute or not paying attention. Anna's probably asleep. Madge is probably eating or sipping on Starbucks at UTM. Everyone else is probably missing in action right now. Or everyone's just burnt out from too much studying and day school. All right. So now my last one is find 2 points on each of the given lines besides the given point. All this really means is sub in a value for your S or your T and give me a different point on the graph. So for example, let's sub in S is equal to 1, which means I get 0, 4 plus 1 times 5, -2, which gives me 0, 4 plus 5, -2. And I'll just say 0 plus 5 and 4 plus -2. And my other points on this line can be 5 and 2. So I have a point 5 and 2. Now, let's take, say, S is equal to 2 and find the second point on that line. I get 0, 4 plus 2 times 5, -2, which gives me 0, 4 plus 10, -4. And what I do next is do 0 plus 10. Sorry, let me erase that. 0 plus 10, comma. Comma 4 plus -4, which means another point on this graph is going to be P at 10 and 0. And now we can do the same thing with my symmetric equation. So I can sub in, let's say T is equal to -1, which means my X is going to be 2 plus -1, which gives me 1. And my Y is going to be -1, which means I have a point at 1 and -1, which is another point on that line. Now I can also sub in T for 2, or 2 for T, and I'll get X is equal to 2 plus 2, which is equal to 4, and Y is always going to be -1, which means another point on that line is going to be 4 and 1. So this is how we can find 2 points on these given lines.